Mercer on Mission is a program unique to Mercer University that allows Mercer students to serve people across the world using the skills that they have developed in the classroom. The programs are conducted in numerous developing countries and are intended to allow students to experience challenges faced by people across the world, while also allowing them to interact with cultures vastly different than their own. In 2014, Mercer on Mission, Ecuador, offered 7 undergraduate science majors the opportunity to interact with people living in a gold mining region of the El Oro province. Ecuador is a democratic republic in northwestern South America, bordered by Colombia, Peru, and the Pacific Ocean. Gold mining has been a major source of income in several provinces of Ecuador, including the El Oro province we visited. Here, more than 20,000 people depend on gold mining to support them financially. The ore and the chemicals used during the processing of ore result in high levels of metal contamination in the air, soil, and water. By understanding the extent of this contamination, we were able to highlight simple solutions and develop systems to address underlying problems with the intent of implementing long-term solutions in the future. Dr. Adam Kiefer and Dr. Kevin Drace collaborated with one of Ecuador's governmental organizations called INAHIM, along with the University of British Columbia, the University of Toronto, and the Federal University of Rio de Janeiro under a United Nations Industrial Development Organization, barely known as UNIDO grant. The purpose of this UNIDO grant is to monitor and reduce mercury emissions in the city of Portobelo, Ecuador. As a part of this collaboration, our group was interested in determining the extent of mercury contamination in the air at processing plants and in the cities of Zaruma and Portobelo. We plan to map these cities with respect to mercury concentration. Doing so will allow us to determine locations of contamination and inform the local community about the locations. In addition to collecting air samples, we were interested in engaging the knowledge of the miners in the terms of the processes they used. We also plan to gather soil and water samples for future analysis from these areas because heavy metal contamination in the soil and tailings pose a threat to the environment and water sources. Also, these samples will allow us to determine the bacterial and microbial populations in the environment.
Before traveling to Ecuador, we dedicated a week to classwork regarding the chemistry of mining in preparation for the trip. To understand the chemistry involved, we first had to understand the gold mining process. The process begins when gold-containing ore is mined and transported to processing centers to undergo various techniques of gold extraction. The first step in processing ore is comminution. Comminution is taking large chunks of ore from the mine and breaking them down into fine particles to liberate the gold. This is achieved using various machines available at processing centers. In Ecuador, a Chilean mill or a chancha is commonly used to crush the ore. A Chilean mill is a large cylindrical tank that uses heavy metal wheels designed to grind ore. Water is added to the crushed ore in the mill to produce a heterogeneous mixture that empties out into a sluice, which is an angled trench lined with pieces of carpet. As the crushed ore passes over the carpet, the heaviest particles that contain the gold collect in the fibers of the carpet. This material is rinsed from the carpet into buckets and then panned to remove unwanted material known as gangue. Mercury can then be added to the resulting material to amalgamate the gold in a method known as concentrate amalgamation. An alternative comminution process involves using a chancha to crush the ore. A chancha is a smaller cylindrical tank that spins and contains large steel rods and or ball bearings that crush the ore inside. Sometimes, mercury is added to the ore in the chancha in a method known as whole ore amalgamation. The resulting material from this technique is also rinsed and panned before further gold isolation. Concentrate amalgamation requires considerably less mercury to extract gold than whole ore amalgamation, and therefore, the mercury waste and air pollution due to mercury is higher in the latter method. This makes whole ore amalgamation more harmful to the health of the gold processors as well as to the environment. Many miners and gold shop owners choose to burn the amalgam to isolate gold from mercury. One tool that can be used to reduce mercury emissions is a retort. A retort is a device that contains mercury fumes while burning amalgams and condenses the mercury vapor into a liquid. The tailings from comminution can then be processed further using cyanidation to extract up to 95% of the remaining gold. The cyanidation process involves agitating the tailings solution while adding sodium cyanide. This reaction oxidizes the gold, forcing it into a solution as gold cyanocomplexes. These can either be absorbed using carbon and pulp and then reduced in high temperature and low pH, or reduced using the Merrill-Crowe process via the addition of zinc dust and subsequent burning to remove impurities and leave solid gold.
In order to determine the concentration of mercury in the environment, we obtain water and soil samples and analyze atmospheric mercury concentration. Soil and water samples are indicative of long-term pollution and require lab instruments for future analysis. Mercury Instruments VM3000 and the Lumex RA915M portable atomic absorption spectrometers, referred to in this video as the VM3000 and the Lumex, were used to analyze mercury concentrations in the air due to artisanal gold mining. By utilizing the Lumex's portability, accuracy, and precision, we were able to conduct real-time environmental monitoring with respect to airborne mercury concentrations from 5 to 50,000 nanograms per meter cube. The Lumex has on-stream and data logger modes for detecting mercury in the air. The on-stream mode allows the Lumex to calculate mercury concentrations without storing data onto the instrument's onboard computer. The data logger mode allows the Lumex to compile and store the mercury concentrations at pre-selected time increments on the onboard computer. Although robust, the Lumex must be handled with great care while in the field because exceeding 50,000 nanograms per cubic meter of mercury can contaminate the instrument. When the Lumex is introduced to a highly contaminated area, an alarm sounds alerting the user to move to an area with lower mercury concentrations. The VM3000 is able to measure high concentrations of mercury, up to 2 million nanograms per cubic meter. The VM3000 also has a data logger function that allows a user to record information directly to the onboard computer. Inside the processing plants, members of our group walked around with the Lumex and the VM3000 and GPS to determine which areas had the highest levels of mercury contamination. The group members with the Lumex, VM3000, and GPS often walked together to ensure the two instruments were monitoring the same areas of the processing plants at the same time. The GPS unit is able to track and highlight routes traveled by the user over time. When the Lumex and GPS times are synced, a map can be constructed with the mercury readings at geographical locations. The GPS camera takes photographs of points of interest like schools, parks, hospitals, and restaurants and immediately marks their geographical coordinates. This allows the user to construct a map not only containing mercury hotspots, but containing information relevant to the people affected by mercury contamination.
The VM3000 was also stationed at a specific point of a processing plant to monitor the concentration of mercury in the air for an extended amount of time. This process allowed for our group to carefully monitor how different steps of the mining process, such as when the chanchas start running or when burning occurs, affected the amount of mercury contamination in the air. Using the Lumex and VM3000, we also obtained data about mercury concentrations in the air away from the processing plants. Throughout our trip, concentrations of mercury in the air were acquired using the Lumex while walking and driving. Walking with the Lumex and GPS was effective when employed in the vicinity of areas of high mercury concentrations. In a small town such as Zaruma that lacks a grid system, walking was the best method to analyze the concentration of mercury in the air. However, driving with the Lumex and GPS allowed for the mapping of the entire city of Portobello, which would be a difficult task to carry out in a timely fashion if we chose to walk. The driving method also allowed for quick discoveries of high levels of mercury concentrations that could be further analyzed by walking with the Lumex, VM3000, and GPS. In order to develop thorough maps, students were required to obtain replicate sets of data by walking and driving the same routes multiple times. The data obtained when driving provided a large picture of the area's mercury contamination, while the data obtained when walking provided a smaller, more detailed picture of a specific area's mercury contamination. In Zaruma, the average concentration was 58 nanograms per cubic meter, and in Portobello, the average concentration was 74 nanograms per cubic meter. While determining mercury levels in the air, we located unmarked local gold shops due to the high mercury concentrations associated with such businesses. We discovered our first gold shop while using the Lumex as we drove through Portobello. Outside the doors of the shop, the Lumex spiked to over 50,000 nanograms per cubic meter, but the average mercury concentration was 27,000 nanograms per cubic meter. Initially, the shop owner was welcoming, but when we returned later with our instruments to collect more data, he closed his gold shop, preventing us from monitoring the concentration of mercury inside.
As we walked around the town of Zaruma using the Lumex, we encountered an area of high mercury concentration that caused the Lumex to reach its maximum detection threshold. We discovered that the spikes were caused by a gold shop where amalgams are burned. This shop is located next to a children's bookstore and a restaurant, and across the street from a school. Understanding the potential danger associated with the proximity of these businesses to a gold shop, we returned during normal business hours to talk with the owner of the shop in Zaruma about his business and his methods, as well as to ask permission to set the VM3000 in his shop to monitor mercury concentrations for the day. He gladly obliged, and we set up the equipment and began logging detailed notes about the flow of customers and how it corresponded with the mercury levels. Throughout the day, the owner spoke to us about various subjects from work to family life and was willing to assist us in our research. At this gold shop, the VM3000 data coupled with our observations showed a correlation between the times at which amalgams were burned and sudden spikes in mercury concentration. Outside the gold shop, the average mercury concentration was 79,000 nanograms per cubic meter. Mercury concentration in the shop occasionally exceeded 2 million nanograms per cubic meter, which is the maximum threshold of the instrument, and averaged 210,000 nanograms per cubic meter over the course of a day. We observed that after the owner burned an amalgam, he carried it back to his desk and placed it in front of a fan that was blowing towards him. We observed massive spikes detected by the VM3000, indicating that high levels of mercury vapor passed directly in front of the shop owner on a daily basis. When we provided feedback on ways to lower exposure to high concentrations of mercury, the owner listened to our suggestions were to move the fan into the back room and to minimize the number of children in the store. However, he was convinced that because he only burns off 2 to 3 grams of mercury per amalgam, the levels aren't high enough to warrant the extra time required to change his current practices. From our interaction at the gold shop, we realized that the owner's reluctance to change his practices means that we must adjust our strategies in the future to minimize mercury emissions. The presence of mercury contamination we discovered using the Lumex and VM3000 prompted us to design a survey to gauge the education of the miners working in these areas. The miner survey contained 38 questions that range from miners' basic biographical backgrounds to their knowledge on the different processing methods. Students conducted surveys in a one-on-one setting at the processing centers. The survey began with a short biographical information section to learn about the miners as individuals. We asked them questions about their family lives, how long they had been mining, where they learned to mine, and what they liked most and least about being a miner. We expected these questions to help us gain an understanding as to why they chose to work in the mining industry and what they thought about being a miner.
The biographical section was followed by questions used to determine individual mining practices and preferences. This was done to understand how frequently the miners worked in the mines and processing centers and what types of safety precautions they took while working in both. After these questions, we asked the miners which method they used to process their ore. We gave them a list of several processes and asked them to place them in order of their most preferred to least preferred method. This section was used to help us determine which methods the miners were most familiar with and why they used them. We also expected to determine the likelihood of them switching to more environmentally friendly methods. Finally, there were questions assessing their understanding of the chemicals used during the processing of ore, their use of retorts, and their overall concerns of being a miner. We asked them about their safety concerns when using mercury, cyanide, and zinc. These questions were chosen to help us understand if they were aware of the dangers and risks posed by using these chemicals. Obtaining interviews was challenging because the miners were often busy and skeptical to work with outsiders. Despite the skepticism of some miners, we were able to gather a large amount of data. The survey results provided primary data about the miners. When asked where they learned to mine, 36% said from their father, 36% said they learned by themselves, and 26% learned from other sources. 47% of the miners we interviewed said they began mining 15 to 20 years ago. 31% of the miners began mining 10 to 14 years ago, and 21% had been mining for less than 10 years. In regards to their safety, over half of the miners surveyed were very concerned about their safety when using mercury and cyanide. When we asked them about their concerns while using zinc, only about 1/4 of the miners were very worried about their safety. We asked the miners how often they used the same processing plant, and 42% said they always used the same plant. 47% used various plants, and 11% did not provide an answer. The most common response to what the miners view as the most important part of the process was recovering the gold, followed by safety, the cost of processing, and environmental pollution. Finally, when asked about their knowledge of retorts, 63% said they knew what they were, and of those who knew what it was, 70% of them said they use a retort while burning amalgams. In addition to surveying the miners, we wanted to obtain information from a business owner that provided supplies for individual miners and processing plants in the town of Zaruma. We asked the owners questions such as, where do you buy your supplies? Who do you sell them to, and what types of products do you sell? The interview helped us gain an understanding of the business aspect of the mining process and allowed us to generate a survey specific to business owners that we will use in the future years.
Scientific research is not inherently service. Service comes through the dissemination of information. Our research is useless if we don't communicate our findings to the local community, as well as organizations with power to promote change. To that end, we took the opportunity to train a local consultant and professor, Dr. Gustavo Rivadeneira, and 2 of his students from La Universidad de San Francisco in Quito on air sampling techniques using the Lumex and VM3000. We also explained the theory behind atomic absorption spectroscopy to give them a better understanding of the instruments. Dr. Rivadeneira and his students were interested in the Lumex especially because they had recently purchased one for themselves. After the training session, they accompanied us on a walk to see how the Lumex and VM3000 monitor mercury concentrations in the air. Hopefully, they can use this knowledge moving forward in the future. A key component of our service project was the relaying of our findings to the mining community as a whole. There are groups that are concerned with the health effects posed upon the community due to mercury contamination and are open to suggestions to minimize mercury emissions. For example, the local miners' union, Aproplasmine, gave us the opportunity to present our concerns and the data we obtained. After we went through the problems and our findings, many people asked questions regarding how to move forward. The El Oro province is in a position where currently the best plan of action at this time is to minimize emission through responsible use, but the people represented by Aproplasmine desire to completely remove mercury from the equation. Unfortunately, there are no practical alternatives for the use of mercury in the gold mining processes that are within the reach of that community in the short term. Each potential solution is costly and would result in the loss of jobs in mining due to the added efficiency of new processes. We will continue to work with Aproplasmine to develop short-term solutions to mercury pollution, while striving toward the incorporation of mercury-free mining processes. In the future, we plan to present updated maps to the communities of Zaruma and Portobello, Ecuador, in order for the citizens to realize which areas they should avoid. The people of Zaruma and Portobello will have the opportunity to stop any building projects in an area with high mercury concentrations, which will help prevent future health problems related to mercury exposure. The data we collected in the field and the information that we learned from miners and gold shop owners in Ecuador will continue to be shared with both INAHIM and Aproplasmine. We also plan to communicate our findings from the soil and water samples that will be analyzed. Finally, we hope to involve and collaborate with the local government of Ecuador. The local officials are aware of what the people of their specific province may need in order to make necessary changes. By involving the local government, we will have contacts that are always in the area and will be able to monitor how successful simple solutions are in the field. This chance to monitor the development of the processing plants may allow us to be better prepared in future years.